There you go. This meeting has been recorded, it just said. So we got 14 participants. So we'll just give it a few minutes. Oh, just another minute. We'll see where everybody is.
Now you can hear us.
I can hear you, yeah.
Okay. They're like
So remember there's the chat window as well, okay?
it's weird. Do you want to change the audio output? Oh wait, what happened to my mouse?
Your mouse
It's over there. There we go.
Go to the right, yeah.
No, it's messed up. I'm actually gonna mute it.
Oh, yeah, yeah.
Okay, so the first thing, this is going to be an interesting experiment, see how it works. First thing I want to ask is, what's the best way to do this? So these are going to be recorded and I'll put them up on YouTube. The question I want to ask though is, do you want them in short segments where each segment focuses on a particular thing, or you just want one long one? Anyone? Anyone? So shall I ask it again? So they have the option here of either I can do a series of short segments today, okay, or we can do one long one.
Okay. What was the question?
So the question is, I can either distribute this class as a series of short segments, say 10, 15 minutes each, and I can do that today, and then I'll upload them to YouTube, or we can do just one long, hour, 20 minutes.
I think the long one is going to be best because we can skip around if you want.
Oh yeah, okay then. All right then. Yeah, okay. All right, we'll try the long one then, okay? So what I've got here, I'm going to do a combination of drawing on paper through the camera, you can see, and then also I'm going to switch to, I'm going to share my screen, and let's see if that works. So I'm going to share the screen. Is it shared? It should be shared now, is it?
Yes, it is.
You can see the PDF basically. Yeah.
Yes.
Okay, so I'm going to do a mixture of, because I don't have any slides, I'm going to do a mixture of going through the textbook and writing on the pad, okay? All right then, so let's begin then, shall we? So
Rather us keep the microphone on, or do we want to mute ourselves?
I'm not hearing any feedback, so
What?
you can leave them on if you want. But if we start hearing any weird stuff, you want to switch the microphones off. Okay. All right. So, when was it? Tuesday. Yeah, it seems so long ago now. We started talking about negative feedback, and I went to chapter 22. Oh, by the way, straight after this, I'm going to upload a list of topics that will be in next week's quiz. Okay. All right. So on Tuesday, then we talked about some of the properties and the desirable properties that you can get from negative feedback. There's the zoom here. Let me zoom in a bit more. That was the improvement to the transient response. There is stability, although it can go bad if you're not careful. It's fairly accurate at tracking a set point. There are changes in sensitivities, meaning that the system is less sensitive to variation in the components of the negative feedback system. And this is exploited a lot, for example, in op-amps and presumably in biology as well. And then you also get this linearization, which at first seems very counterintuitive, but if your amplifier is nonlinear, if you add negative feedback, it'll basically linearize the nonlinearity. Which is a great thing to have if you're building an audio amplifier or something like that, where you have to faithfully reproduce the input signal, but you want the signal to be bigger, okay? So I tried to come up with a succinct statement about, what is the role of negative feedback, and I thought, feedback is basically used to combat the effects of uncertainty. I mean, some of these things may not be to do with that. I mean, improving the transient response is not that. But overall, feedback is often used in many places to combat the effect of uncertainty in the components that are used to build the feedback system. And so this is you've seen this before, this is a generic diagram of a feedback system. And if you remember way back, there were different ways in which to feed back the signal. The common one, I guess maybe it's not common, but the easy one is the proportional feedback. And this is what proportional feedback here is. So we have a set point on the left, we have the output on the right, and then we have the feedback going back to the set point, and we get a difference computed between the set point and the feedback, and this gives us an error term E. Now, it depends what you do with that error term. And there are three things you can do with the error term. You can multiply the error term by a constant, Kp, and feed that into the amplifier. That's called proportional control. You can feed in the integral of the error, that's integral control, or you can feed in the derivative of the error. And you can combine all three by summing them up, and you end up with something that's called a PID controller. All right, so let's focus on proportional control. That's the easiest one. And the first thing I mentioned last time was this idea that you get an improvement in the transient. So a feedback system will respond faster. It's more responsive to faster changing signals. So that means if you inject a sine wave into a negative feedback system, it can cope with higher frequencies than a system without negative feedback. And I had this little simple system here, and I had the rate of change of x was some function of the forward rate minus the degradation rate. And notice I don't have to know what the actual V1 is, all right? All I have to, because I'm going to linearize, I can just derive the derivatives. And so if I linearize this differential equation, I get this one here. Notice I have delta x on this side, and I have the two derivatives here. That represents the A matrix, right, in the linearized equation. And then this piece here, this piece here represents the B matrix.
Sorry.
Yeah, go ahead.
Could you zoom in on the PDF?
Oh, yeah, sure.
Just a little bit.
Yeah, no problem.
Okay, thank you.
Is that better?
Yes.
Are you watching it from your iPhone? And therefore you need a microscope. That's what it is. But that's fine. That's good. So yeah, if you have any questions, right, just say something, okay? All right. Because I can't see you in the audience with frowns and funny faces anymore, so I don't know whether you understand this or not. Okay, so I'll start with this differential equation. I linearize it. This is a standard linear differential equation, this thing here. And it's easy to get the solution for this. So we see here this component is the zero input component, and this is the zero state component. And I've got this term alpha here, which is basically the A matrix, which is the Jacobian matrix, okay? And the alpha term is e to the power of the alpha term. And if you look at the signs for these derivatives, they're negative, right? So dv1 by dx is negative because x inhibits v1. And then the other derivative, although it's positive, is a negative sign in front of it. So both of them are negative. So alpha is less than 0. And if it's less than 0, that just means that this component here decays. All right. So if you apply a disturbance delta x0, that delta x0 will decay at a rate given by alpha t. And with negative feedback, of course, I get this extra term that gets added onto alpha. So with additional negative feedback, it means that alpha is bigger, and since the absolute value of alpha is bigger, and since it's bigger, that means that this decay rate is faster. So this shows you just from this little example that adding negative feedback does make the system act quicker. So the first thing is that negative feedback can increase the responsiveness of a system. And this has also been shown experimentally. There's some famous synthetic biology experiments that were done some years ago where they did just this and they got a better response. In terms of the frequency response, you'll also see this in the frequency response. So you can compute the frequency response using this relation, which we've seen many times now. And you can compute and you'll get this. This is the transfer function. And again, you see there the Jacobian is in the denominator. I can compute the amplitude for this. This is a complex number, remember, and I can compute the amplitude. This has a phase and an amplitude, and I can compute the amplitude, and you get something like this. And you can plot that then as a Bode plot, and you will get something like this. So the red line is when there's no negative feedback, and the dotted line is when there is negative feedback. And as I said on Tuesday, you have to make one adjustment so that you're comparing apples and apples or oranges and oranges. Whenever you add negative feedback, you lose gain. So in order to make a fair comparison, I'm increasing the input, so I restore the gain of the original system. And that's why these two lines here merge into one, all right? So they're starting from the same gain. So if you do that and you do the comparison, you see now that the dotted line extends further out from the red line. That means it can respond to higher frequencies on the x-axis. And so again, it shows you that the negative feedback is more responsive to signals. So we can say negative feedback improves the frequency response of the system, but generally at the expense of the gain, but you can restore the gain by just increasing the input. So it's not such a loss in the end. And this is just to show you, you do lose gain when you add negative feedback. Remember that the transfer function at 0 frequency is the derivative dx by dp, right, whatever your input is. And so if I take the transfer function and set the frequency to 0, I'll get this derivative, which is this, and this derivative is effectively the gain. So that's the point on the y-axis when the frequency is 0, and you can see it's divided by the Jacobian, and of course the Jacobian, the size of the Jacobian increases with the strength of the feedback. So as you increase the strength of the feedback, the gain goes down. So you know, as I said, it's easy to restore the gain just by increasing the input. Perhaps that's not always possible, but it can be done. And they did this when they did these synthetic biology experiments. They basically added the feedback, they lost some gain, and then they increased the input to restore the gain. And then they did the transient experiments, and they noted that the feedback responded much faster. Okay, so then the other take-home message is feedback reduces the gain of the system. Something else that I want to talk about is accuracy. So let me just go back to this list. This was the original list. So the transient response. So let's talk a bit about accuracy, which is something I didn't mention on Tuesday. So let's talk about the accuracy. So there's a section here on accuracy. And by accuracy, I mean how close does the output match the set point? All right, so if I apply a step input to the set point, how well does the output X match that change? All right, so that's what we mean by accuracy. If the accuracy is perfect, there should be no difference between X and the set point. All right, so how are we going to compute that? Well, we'll start off with this block diagram, and the transfer function is given by this. This is a standard transfer function for a negative feedback loop, and hopefully you've seen this thing before. The K times GS is called the loop gain. All right, this is a very important term. I've pulled out the set point input here just to show you that this is the transfer function for the negative feedback loop. So if I pull the set point back onto the right hand side, I get this expression. So X equals this. Now the error term, right? The error term, which is the difference between the output and the set point, is basically what I want to measure. This is going to give me a measure of how accurate the system is. The smaller the error, the more accurate the system is. All right, and if the error is big, that means it's not very accurate. Now, the accuracy is at infinite time, though. So in other words, I apply an input step to R. I then wait for the system to settle, and then I look at the error. Okay, and so if the error is close to 0, I know that X has settled close to my set point. Okay, so I need to compute what the error term is, and the error term is just the set point minus whatever's coming in here. Okay, and so the error term here is the set point minus whatever's coming in. Whatever's coming in is k times x, and of course I know what x is because I have it here, so I can substitute the x in, and I get this relation here. I'll do some rearranging. I end up with this. So that this gives me a measure of the error, all right? But as I said, I want to know what the error is once the system is settled, okay? And it settles at infinite time, all right? Now, how do we, in other words, a steady state, and how do we compute the steady state for a system from the transfer function? Well, we use the final value theorem, right? Remember that, right? So this theorem states that the value of the whatever we're looking at in time, at infinite time, is the limit of s times the transfer of that entity as s goes to 0. Okay, so that's just this theorem, the final value theorem. So we can apply that. So I'll take the ES, which is this. I'll put it into here, and I've got to remember to multiply by s because that's part of the theorem, and I get this. Okay.
All right, Dr. Soro.
Yep.
Could you explain why we multiply the input by k when we calculate the error term?
Do you mean this here?
Yeah.
That's because this block here is the gain of the feedback, and what's coming into the block is the output, right?
Oh.
And
yeah.
so what's coming out of the arrow here then is k times x. One thing we haven't done much, and unfortunately, is block diagrams. There's a whole thing on block diagrams. I haven't found them that useful myself, so which is why I haven't gone over them much. But this is a block diagram. You can represent a transfer function in terms of a block diagram, and there are certain rules for reading block diagrams and for extracting expressions from block diagrams. And one of the rules is the output from a block. For example, this piece here is the block times whatever's coming in. All right.
Okay.
And so if I want to know, so my error then is the set point minus, right, whatever's coming in this arrow. Whatever's coming in this arrow is k times x. Okay, but I know what x is. I know what x is though, so I can just swap x into here, and I end up with this. So that's all. That's all I've done there. In this case, I pulled the r out as well there as well. And anyway, I simplified this, which ended up like that. Okay. So now I need to calculate what the error is in the time domain at infinite time, because that'll tell me how much error there was ultimately. All right. In order to do that, then I'll invoke the final value theorem. That'll give me the value of the error in time, in the time domain. Right. Remember, the final value theorem is for converting the final value of the system, the steady state value of the system, expressed in the as a transform into the time domain. Right? It's a very nice shortcut. So I don't have to explicitly take the inverse transform of this and then take t to infinity and things like that. So this theorem is just a shortcut. And the shortcut is you take the limit, s goes to 0 for s times whatever your transform is. In case our transform is e to the s, and I can substitute that in, and I get this expression here. So I need to evaluate this as s goes to 0, but I need one other thing. I need to state, well, what is your input? I mean, what are you actually comparing against? And so I'll just say, let's make the input a step function. That's a convenient one. I want to know how x tracks a step function. And of course, we know what a step function is. It's 1 over s, right? I can make it a unit step function, keeps things simple. So I'll substitute rs for 1 over s, and that's all I've done here, all right? And now I can take s goes to infinity, goes to 0, sorry. G of s turns into g of 0. And of course, s divided by s, in the limit, they approach 1, even though s goes to 1, okay? And this is basically my answer, all right? Now, if I take this this is the loop gain again, but it's the loop gain at 0 frequency. If I take that and call it Kp, okay, I end up with this. So this is my steady state error, right, as a result of proportional control. And you notice it's not 0, right? It's 1 over 1 plus Kp, right? And it's determined by basically the strength of the proportional control and also the gain from the amplifier itself. Now I can push the gain up and up and up if I want. I can keep on increasing the strength of the feedback. That means increasing the value of Kp, and of course this then will tend to 0. So I can, using proportional feedback, I can make the error go to 0, but it means ramping up the negative feedback. And because most systems, this is a first order system, because most systems aren't first order, if I try to do that on a non-first order system, I'm probably going to start getting either damped oscillations or oscillations. And so you can't actually ramp up the strength of the negative feedback. It doesn't really work because you get these side effects. So we can say though that, you know, if you increase the loop gain moderately, don't go crazy, you will improve the accuracy of the feedback response. Okay. Now I don't think, let me just check here. Do I have the I don't have the little little simulation I've got for the car, but you can play with that and you'll notice that the difference between, you know, the speed you want and the speed the car is actually giving you can be narrowed as you increase the strength of the proportional control. But eventually you can start seeing it ringing, it starts oscillating, and then eventually it goes into full oscillations, and of course your car is in trouble. So, all right. And as an example, we can compute the degree of error. Let's say your system, your loop gain is given by this, okay, 90 over s plus 10. We can apply a unit step to this, 1 over s, and I can compute. I can just use the final value theorem, and you go through all this, take s to 0, and you get 0.1. 0.1, basically, you can interpret as 10%. It's 10% of the set point, right? Because we made our unit step, or our step input was a unit. So this is relative to that. So in this case, given this transfer function, I will observe a 10% difference between the set point and the output. All right. So you can use that to actually compute how accurate your negative feedback system will be. All right. Any questions on that? I think that's straightforward. So, I mean, there are other inputs we can apply, you know, not just a unit step. We can apply a ramp, parabolic, and those are the two common things that are applied. We're not going to go into detail here, and this is not going to be in the quiz, but I do want to mention this. Let me scroll down to this table, which summarizes the results, okay? This is, and they often classify these responses into types. All right, so type 0 is basically a first order. Type is a first order transfer function. Type 1 has effectively one integrator, and type 2 has 2 integrators. Now, so let's just look at type 0, which is what we just looked at. So we're going to apply a step response, a ramp, or a parabola. And so for a step response, we already say that the error is A, because I have A now because that's the gain. It's not unit step, but a unit step of size A over 1 plus Kp. For a ramp, it can never track it. Right. So if you have a signal, if your step size is increasing in the form of a ramp, basically your output will never catch up. It can never catch up, and so that's one of the issues again with proportional control. Same goes for parabolic. Now the solution, of course, to this is what? Does anybody know? Does anybody know what the solution is?
Put it to go in there.
What's that?
an integral in there?
Yeah, stick an integral in there, yeah. So if I have a little proof back here, sorry, we have to go all the way back here. Where is it? Here. So if I apply an integral and put an integral in front of it, right? So instead of proportional control, we'll have an integrator. You can compute the errors again, right? This time we're putting a 1 over s in front of the amplifier, okay? And if you do that, the error at infinite time goes to 0. Okay, and that's pretty much irrespective as well of the input signal. So that's why integral controllers are so popular, because they can do that. Okay, oops, where am I going? So that's aspects of the accuracy, and in terms of the quiz, it's basically the accuracy for a first order system that has say a step input. Okay, so that's what might be asking in the quiz there. As I said, I don't worry about the different details of the different inputs, other than the fact that if you do try to apply, sorry, where am I? This table. If you do try to apply other inputs, you'll discover that a simple proportional controller on a first order system can't keep up with the input changing. So, okay. The next one is linearization. I've talked about this before. It's a pretty simple idea. This is the equation again for the feedback system. And as I said, if the loop gain goes up and up and up, this simplifies to basically AK. If you increase AK higher and higher and higher, eventually the 1 becomes insignificant, and you can cancel the A's out, and you get Y equals R over K. All right, and so in other words, the output is proportional to the set point. So you get this linearization, and that's used extensively. Here it is, I guess. And that's used extensively in audio feedback amplifiers. So. You can do some other tricks with this kind of thing. There are other tricks here, not so important, but you can assume that the amplifier is nonlinear. And if you do that, you can also show it doesn't matter what function the amplifier has, so long as it has sufficient gain, as long as the feedback is strong enough, that'll insulate you from any nonlinearities in the amplifier itself. So,
Dr. Thur, I have a quick question.
Yep.
So you talked about accuracy, but is precision also like how does precision fit within systems?
Precision. Well, I guess. I mean, I don't know if it makes any sense to talk about precision in terms of this. I mean, you talk about precision in terms of measurement, of course, but I'm not sure what it would mean. What would it mean for a feedback system? I mean, accuracy is basically how close you are to the true value, right? And precision is how, if you are at a value, how spread out you are across that value. Now, I guess one could argue that because these systems are noisy, I suppose, and there will be I mean, you won't get a single point on the output. There will be a distribution of outputs. So let me just go back to make sure everybody knows what I'm talking about. So if you have this feedback system, so the question is, how precise is X? X may be close to R, but how precise is it in the sense, if I looked at it at multiple times, what kind of distribution do I see in X? So that's a kind of different question, and you'd have to answer that within probably a probabilistic framework. You'd have to look at what noise is coming in on the set point, what noise do we have in the amplifier itself, and so you'd have to ask that question from that point of view. So I haven't seen that actually, and it's an interesting question, but I've not seen it asked actually, so I can't tell you the answer to that, but it'd be interesting to know, because you'd like to know how robust is your feedback system in terms of precision. So not something I've come across. Okay. The other thing you could do, which you'll find in the textbooks, they talk about sensitivity as well. They ask, okay, so the system is accurate, but how sensitive is that accuracy to, say, disturbances you apply to the system or variation in the components in your amplifier. And the one way to do that is to say, well, I'm going to apply disturbances are going to come in, if you can see that, are going to come in by disturbing Y, the output, all right? And so I can put another sort of summing junction in here that takes into account the disturbance. And I can rewrite the equation with the disturbance there as well. Let me see, let me make sure I got this right. Yeah, okay, that comes down later. Let me just show you though, first of all, what about variation in the amplifier itself? So what you can do is you can ask, how does the output of the amplifier, sorry, how is the output affected by variation in A? So I can actually just compute this derivative dg by dA. I can take this expression, which was derived previously, take the derivative, and I get an expression like this. I can scale it at that if I want, and I'll get the scale version. Basically what it means, again, it means that the higher the loop gain, the less sensitive the system is to changes in the amplifier. So, which is not unexpected, I guess. All right. So the more feedback, the more robust the system is to just normal variation in the amplifier performance itself. So, and these are all saying the same thing, really. There's just different ways of looking at it. You can do the same thing with disturbances on the output. So, and you can imagine disturbances in the output coming through. Maybe the output is picking up ambient AC signal from the surrounding, AC wiring, and that may be bringing in noise into the system, and you want to know how that might be influencing the output. So you can take into account that there may be disturbances at the output, and you can add that to the equation. And again, you can then differentiate it and get the derivative of the output with respect to the disturbance. And again, you find the same sort of equation. The higher the loop gain, the more resistant the system is to disturbances on the output. Okay. So it's a really win-win situation, negative feedback. And as I told you, when Harold Black, back in, was it 1929 or something, first proposed this, nobody believed him. The patent office wouldn't award him the patent because they said this can't be right. Took them 7 years to change their mind, because by then they'd actually built the things, and they actually did work the way he predicted. Okay, let me see. What's this? Let me see. I want to make sure. Yeah. Sorry, I'm flicking fast through here. So we've done this. I don't need to do that again. What I really want to talk about is stability. Okay. So I want to talk about stability. Now we've already mentioned this a few times. The single unit. Let me scroll along here. So a single unit is stable. A double unit like this is stable. And just let me go through this one again, this double one. So to show that whether this is stable or not, we have to compute the transfer function, or in particular, we have to compute the determinant of this matrix, and this is the Jacobian. Okay, so we're looking for the determinant of the Jacobian. Okay. So let's compute this then for this system. So I need the stoichiometry matrix, and I need this dv by dx matrix. The I matrix will be a 2 by 2 because we have two variables, okay, x1 and x2, all right. So I can write down the stoichiometry matrix. That's pretty straightforward. Now I'm going to do a trick, all right, which I didn't show you last time. And in order to do that trick, I need to show you something. I'm going to bring on another page here from, this is page 100. And I want to remind you what the elasticities are. So the elasticities are these, they're the derivatives scaled, okay? They're the derivatives scaled, all right? Now what I'm gonna do is I'm gonna rearrange this equation to get the derivative on one side and the elasticity on the other, okay? And if I do that, I get this. So I'm gonna define, because I need a symbol for this, I'm gonna call, and there's a typo there, that actually should be a derivative. I should rewrite that down so I remember. That's page 100. Should have derivative. So that's dv by dx. I'm going to call that this fancy epsilon, okay? So in rearranging the elasticity term, right, I have the simple derivative on this side, then the scale derivative here, and then that's the scaling itself. So I've expressed this is just a rearrangement. I've expressed the actual derivative in terms of the scale derivative and the scaling, all right? So remember this for a second. So we'll go back to here. All right, and now I'm reminding the reader I'm defining this just to be the simple derivative, dv by dx, okay? So I'm going to write dv by dx like this. So I'm not going to write down those, you know, all the explicit derivatives. I'm just going to write down this fancy e. Notice some of them are 0. They're 0 because, well, let's have a look at the first one. This is epsilon v1 x1. So remember that. Actually, maybe I should, actually, this is a moment to switch to camera, I guess. Stop sharing. Are we there? Oh, yeah, here we go. So, here's my pen. Pen. Here it is. So I'm going to define this fancy. Oh, look at that. Can you believe it? Do you see what's happening?
Yeah.
Dear. Sorry about that. We'll have to fix this for next time.
What are you talking about?
What's that?
It looks great though.
What? Say it again.
It looks great though. What are you talking about?
Well, for me, it's inverted.
Oh. It's normal for us. It's
Oh, really? It's normal for you?
yeah.
Oh, okay. Oh, in that case, everything's inverted for me. Oh, okay, good. How strange. Okay, so that's going to be my fancy e, okay, and that's going to be dv by dx, okay? And I'm going to define, then I'm going to also define that to equal the scaled one times v divided by x, okay? So I need to go, I need to bring up my, where is it? Hold on for a sec. Just going to move this to the other screen, okay. So when you look at the matrix, when I looked at the matrix, the top left-hand one was 0, and I just want to remind you, and this one, this was this fancy, start again. There's the fancy E, and that was 1, 2, okay? And so if I look at the, if you look, let me bring this over again. Maybe I can do, oh no, you can't see it at all. But this one here was x2 affecting v1, and so I had, let me draw it like this. So that was x2. That was affecting that one, okay? So number 2 did affect number 1, so there was a value here. This one, though, was epsilon 1, 1, okay? And in terms of this little diagram, I'm saying this is not happening, okay? There's no interaction, immediate interaction from x1 back to that one, so that's 0. Okay. All right, so let me then go back to share, bring this on. Oops, hold on. Share, thank you. All right, so if I do all that, I take all that into account, I'll get these entries. I'll get 0, an entry, 0, 0, entry, no entry, entry. All right. So you just basically look at who's affecting who. And now what I'm going to do, I'm going to do this trick. Every time I come across this fancy epsilon, I'm going to substitute it for this. All right. So remember, I just showed you that.
So are you scaling it or are you unscaling it?
I'm just doing a substitution. So I'm taking. So remember, this is the elasticity, okay? All right, and all I did was I rearranged this so that the derivative was on the left-hand side, and the epsilon was on the right-hand side. And then I'm going to call the derivative this fancy epsilon. Okay, so when I do that, so I'm going to call the derivative, that's a derivative, by the way, I'm going to call it this fancy epsilon. Therefore, this fancy epsilon is the elasticity, which is scaled, times these things. And these things are, all they're doing is unscaling the elasticity to get me the unscaled one. That's all they're doing. Right? So this is just a trick. So every place I see one of these, I'm going to swap it for one of these. All right, that's all I'm doing, okay? So if I do that, I'll take each one of these fancy epsilons and I'll swap it for one of these, okay? Now, for many of these elasticities, their values are actually 1. So maybe there's going to be another change in notation here. I'm going to call V1 over X F. Right, so the ratio of the velocity to the concentration I'm going to call F, because this just saves me lots of writing, okay? So epsilon 1 to F1 is this, where I've taken V over X and turned it into F1, okay? Now for these other ones, you notice there's no epsilon. That's because in all these cases, I'm going to assume first order kinetics. So all the elasticities must be 1. So I can just leave out the epsilon. And since I said I'm going to call V over X an F, I just leave F's here. All right. So this sort of simplifies the notation a bit. So with this in place, I can now compute this term, because I'm going to compute the determinant of this. So this term is just now, so I multiply this whole thing here by the stoichiometry matrix, right, to get you that, and I subtract it from the identity matrix multiplied by S. And if I do that, I get this thing. So what I'm after is then the determinant of this, and the determinant of this is just the product of the diagonals minus the product of the other diagonal. All right, and I end up with that. Okay. Oops, sorry, I end up with that. So in order to determine the stability of this system, I need to know, what are the solutions to this system? All right, in other words, what are the values for S? All right. And I don't know if you remember, but it says here the criterion for negative roots and hence stability in a quadratic equation is that all coefficients have the same sign. So we have to check, do the coefficients have the same sign? Well, this one's +1. Now, what about F2 and F4? Are they positive or negative? Well, what were the Fs? Well, the Fs were V over X. X is the concentration of X. Concentrations, of course, have to be positive. All the reaction rates are positive. Proteins are being made at a positive rate. Proteins are being degraded at a positive rate. So the V's are all positive. So the ratio is positive. So all the F's are, in fact, positive. So F2 is positive, F4 is positive, and the sum, of course, must be positive. So this coefficient is positive, right? What about this one? So, well, as I said, F2 and F4 are positive, so the product must be positive. F1 and F3 are also positive, and the product is positive, but I got a negative here. But this elasticity is negative because X2 represses V1, because that's the feedback term. So negative means positive. So all the coefficients are positive. Hence, all the solutions to this quadratic equation must be negative. Okay, hence this system is stable. Okay, so in fact, no matter what you do to the system, you can up the gain, to infinity if you want. It'll still be stable. Okay, so that's nice. So this one is stable. Okay, now how about we move? So any questions on that? All right. So let's move on to a 3-step pathway. So 3 genes. Okay, and people have actually built these ones, and surprise, surprise, these ones actually do oscillate. Now we can go through the same process. Here's the stoichiometry matrix for this new system. This is the dv by dx matrix. Again, I've taken out those fancy epsilons and swapped in elasticity f, okay? Let me see, so x, so this one here, the v1 x3 is actually the negative feedback, is the negative feedback from x3 all the way back to v1. Let's pick another one, this v4 2, so this is species 2 and how it affects its degradation. So all these degradation rates are going to assume a first order. So a lot of these will drop out to be as ones, and we're left with f's, just as it happened before, in fact. So yeah, I did this substitution, right, which gave me all these. I'll multiply out the matrices, okay, and when I get this, for some reason I haven't simplified it yet. Oh, there I have simplified it. So all the elasticities except the feedback one have a value of 1. So all these elasticities, they just drop to 1, and I'm just left with f's. And as before, all the f terms are positive because they're just the ratio of a reaction velocity to a species. All reaction velocities are positive. All species have positive concentrations, obviously. You can't have a negative concentration. So now we have to work out the determinant of this one, right? And that gets perhaps a little bit more involved. This time you get a cubic. So here's the cubic equation. Now the rules for, and this is related to the Routh-Horowitz rules as well. The rules for figuring out whether this matrix admits negative solutions is, where are they? Here we are. So let's look at this general quadratic. Okay, so if a general quadratic, the condition for all negative roots for a cubic like this is a cubic. I stopped calling it a quadratic. The condition for all negative roots is that all the coefficients are positive as before, but we have this extra condition, a1 times a2 must be greater than a0, a3. Okay, so first of all, we can look at these three conditions. So let's look at a0. A0 is the one in front of the cube. So this is the cube. Obviously, the coefficient here is 1. Obviously, that's positive. That's positive. This is the sum of all the f terms, and the f terms are positive. So the coefficient here is positive. The coefficient in front of a3, right? A3 is this one here. This is a3. Okay. This one is actually also positive because F2, F4, and F6, they're all positive, so the product is positive. This is the negative feedback term, and that's negative, but there's a negative in front of here, so the whole thing is positive. So this whole thing is positive. So we've satisfied these three criteria. Now we need to figure out this one, and this is the one where it gets a little bit more complicated. So we have to form the product A1, A2, A0, A3 and figure out whether this inequality is true or not. So this is so in constructing this, I actually end up with this. So this piece is A1. So if I highlight that, then highlight this, that's A1, that's A1, okay. A2, that's this piece here, and that's the same piece as that one up there. And of course, A0 is just 1, and A3, of course, is this whole term here, which is what we see here. All right. Okay, so what I'm going to do now is I'm going to divide both sides by F2, F4, F6. I'm doing that because I see F2, F4, F6 on this side, so I can get rid of it there. If you multiply this whole thing out, you'll find there will be F2, F4, 6 appearing there, and you'll be able to simplify this entire left-hand side to look like this. And you end up with a 3 as well. And of course, this 1 just comes from this piece here. All right? So this bit is quite straightforward. Divide both sides by F2, F4, F6, and you'll end up with this. I'm going to subtract 1 from both sides. So that removes the 1 from this side, and I subtract the 1 from this side. You have to be careful here. You have to know your rules for manipulating inequalities, okay, which are not always the same for equality expressions. So you just have to be careful there. But anyway, I subtract 1 here, I get 2 here. So I now end up with this. Now, what's interesting about this expression here is, I mean, I know they're all positive, and then it's a +2, and it's got to be greater than this. So this is, remember, this is the condition for stability, okay? You have to remember that this is the condition for stability. And the question is, what kind of values can this have? Well, if you notice, there's actually a pattern here. There's F2 over F4, then is a 4 over 2, right? So they're inverted. There's a 6 over a 4, then there's a 4 over 6. So they're a pair like that. Then there's a 6 over 2 and a 2 over 6. So there's actually a pattern of 3 groups here. Now, you can figure this, you can figure out the limits of this. Then this expression does have limits, right? It has an upper limit, in fact. One way to do this is the brute force way, I suppose, is just to randomly assign values to the f's and see what this expression looks like, just in terms of numbers. And if you do that, you get this equation. So what this is saying is, if I randomize F2, F4, F6, F2, F4, and F6, just give them random numbers. They've got to be positive though, right? And I put those numbers into this expression, I will get the number out on the y-axis. Now what's striking here, of course, is that this is actually 8. Below this, the value of this term is 0. Right? So, I was going to say, yeah, and if there are other combinations of this term which give me numbers greater than 8, I get an actual, positive number. So this means that, well, let me look at this in another way. Notice what this pattern looks like, right? I'll take this pattern, okay, and I'll re-express it like this. All right, this thing here is exactly the same as the pattern, because what we have here is this is basically the inverse of this, right? This one is the inverse of this one. This one is the inverse of this one. All right, so it's a plus, so it's 1 over a plus a. All right, so I've got 1 over a plus a, and it's not too difficult actually to figure out that this sum will always be greater than or equal to 2, always. All right, so you can imagine it, if a is 1, okay, then 1 over 1 is 2, so that equals 2. If I try to drop a, because this increases now because it's 1 over a number smaller than 1, and if I increase a, this becomes a number, what does that do? That makes it smaller as well. You can show that this sum can never drop below 2, right? Never drop below 2. So each of these terms here can never drop below 2. So this can't drop below 2, this can't drop below 2, this can't drop below 2. And of course, the sum then can't drop below 6. All right, so it can't drop below 6. And in fact, if you add the 2 on, of course, this entire thing can't drop below 8 to be true. All right. So for stability, remember we're looking at the condition for stability. And so that 8 actually matches this 8 here. All right. Okay. So what have we got then? So what I'm saying then is that for stability, let's see, so yeah, the lowest value for each term is 2. The maximum for the sum of 3 pairs is 6. With the addition of the remaining 2, the minimum value on the left hand is 8. All right. We therefore summarize that if the value of the elasticity, the negative value of the elasticity, is less than 8, then the system is stable, right? This is the condition for stability, okay? Remember that this 8 can't drop below 8. It's impossible for it to drop below 8, okay? So for example, if my elasticity value was -2, okay? -2 minus is 2. 2 is less than 8. Therefore, this system will be stable. Now, if the strength of the negative feedback reaches -8, we've reached a threshold, because if the strength of the feedback goes, say, to -8.1, this inequality is violated, and immediately we can say it's no longer stable. Okay, and the system is unstable. All right, so if I set the elasticity to -10, -10 minus is 10, and 10 is not less than 8. Therefore, this is not stable. So this is actually quite an amazing result. It basically says if your elasticity is between 0 and -8, it's going to be stable. If your elasticity is below -8, like -9, -10, whatever, thing will be unstable. And you can do a simulation of this, and it really works very nicely. You can keep increasing the strength, and suddenly when it hits -8, it flips to instability. Okay, now you can extend this to any length pathway. This is just up to 3. The math gets a little bit more involved. This is some hardcore research. You can generalize this. So I can generalize the stoichiometry matrix to any size. I could generalize the matrix of elasticity coefficients to any size. So I can then generalize the product. I can also generalize the Jacobian. It becomes, well, it's not it's SI minus N over dV by dx. I get this. I can generalize that. I can set all these elasticities to 1 like I did before. I can say all the F's. I'm going to make one more assumption, because otherwise it gets even hairier. I'm going to say all the F's are equal to each other. That basically just means that the ratio of the velocity to the concentration is the same. I can do all that, and I basically end up with this quadratic equation. Sorry, this polynomial equation, and it's now got of course an order of n. All right. It's very hard to compute solutions to systems of arbitrary order. In fact, above order 5, you can't. And so various tricks were done, and I'm not going to go through these tricks. But you end up with this relation basically involving cosines. So this is the stability criterion for a system of any length. I guess one thing to notice is that it's much less stringent now. It's not 8 on this side, but it's a 1. Okay, so this implies that it's actually easier for a longer system to oscillate, and that is indeed the case. You can use this expression to calculate a table and to find the instability threshold. So for 1 gene, it's always stable. For 2 genes, it's always stable. For 3 genes, the threshold is 8. So if you can make your feedback have a strength of 8, then stronger than that, it'll be unstable. If you have 4 steps, you drop by half and you go down to 4, which is much more realistic. Okay, and so on, and it gets easier and easier for the thing to oscillate the longer the cascade is. And in fact, in the limit, which is I guess a bit of a silly limit, but if it's an infinitely long gene cascade, you can actually get instability if the elasticity strength is just 1. Okay, so all right. Okay, now I don't expect you to definitely not to know this proof. I will expect you to know to understand the 3 variable system, the 2 variable system, and the 1 variable system. Okay, I don't expect you to be able to do any calculations on anything more than 3. All right, so and this is actually quite a hard. In research, this is quite hard, and it's taken like 50, 60 years to get to this point. In fact, what people are doing now is they're no longer, I guess the algebra is too hard. They're not doing algebra anymore. They're actually doing really large parameter simulations to try to find the upper and lower limits for systems like this. Because I put in some restrictions here, for example, that all the elasticities here from step to step, or 1, which may or may not be realistic. I also made this rather unusual condition that all the f's have to be the same. There's certainly no guarantee that's going to be the case. And people, I don't know, maybe people do less algebra today, but these days with computers, they just ask the computer, try all combinations and tell me what you come up with. But anyway, okay. So, okay. So let me see, what's the time? Okay, so the last thing, I'm going to finish off here then. So the last thing I want to consider, and I'm going to switch back to the camera when we stop the sharing. Any questions on that though before I go on? All right, okay. So what I want to talk about now is why, talk about it in more detail. I mean, I hinted at it on Tuesday. Why do these things oscillate at 3 steps, but not 2 steps and 1 step? Okay. And it's all to do with the phase shifts that occur in 1 step, 2 steps, and 3 steps. And as I said before, for one step, you just get a -90-degree maximum shift. Okay. For a 2-step, I'll get, that's 0. For a 2-step, I'll get 180. And for a 3-step, I'll get -270. And it's something to do with this. And it really hinges on the loop gain. So remember I had the output was, it was the, whatever the input was, times the amplifier divided by 1 plus k times the amplifier, okay? The crucial thing is the loop gain, all right? That's what the loop, and is what the loop gain does. So what I'm gonna do is here. Let me see if I can do it. It might take me a few attempts to do this, because I know this is not actually in the book, so, or parts of it in the book, but not everything. What I'm going to plot here is a Bode plot. I'm going to plot frequency here, of course, amplitude here, and phase there. Okay, and I'm going to mark here the amplitude, the unit gain amplitude. Okay. All right. Okay, let's see. All right. Okay, let me first draw this. So that's the Bode plot for the amplitude, and you notice it crosses the unit gain at this, whatever this frequency is here. Okay, crosses the unit gain there. Above this, a signal can be amplified. Below this, the signal will be attenuated. And I should emphasize, this is the Bode plot for the loop gain, not the entire feedback system. All right. Okay, so what about the phase plot? Well, the phase plot, and this is what I got to be. So what I'm going to do is I'm going to mark here. I'm going to mark here the -180 point. Okay. All right, and let me get this right. Okay. Yeah. So I'm going to draw it like that. Okay. All right. So if you see that. This is the point where it crosses the 180-degree mark. And if I extend this, if I've drawn it right, if I extend this up, I just did it. It matches at this frequency, right? I see a -100-degree phase shift when it's slightly amplifying, okay? I meant to exaggerate that a bit more, but it didn't work out, all right? So it's slightly above unit gain. So what we've got here is a system where the phase between the beginning and the end of the cascade of changes is 180, -180. The gain of the system is greater than 1, so signals can be amplified. The other thing we have is not to forget is that this thing here provides an additional -180 degrees, right? Because it's repressing. So this piece on its own gives me 180 here, but this additional piece gives you another 180. And what effectively that does, it basically turns what was negative feedback into positive feedback. And so instead of now dampening things out, it starts to push things away. And because we're also in an amplifying region, that whole thing starts to expand. And basically you end up with an instability. Now, it doesn't keep on expanding forever because it reaches certain limits in the system. These gains, remember, and the phase shifts will change as it starts to expand. And what will probably happen is, most likely what will happen is the gain will drop below 1 and it starts to start contracting again. And as it starts contracting again, it comes back to this point again, and the gain has gone above 1, it starts to expand again. You see this contraction expansion all the time. And so what you're seeing is amplification. So the two criteria for oscillations are, there has to be a crossing point, an exact crossing point where there has to be a crossing point where you cross over the 180-degree phase shift, okay? And at that point, you have to have amplification in the gain itself. If you have those two conditions, you'll get oscillations. If you don't, you won't. Now, why is it so important for this? Actually, it has to be a crossing point, because I need exactly 180, because I'm having to add it onto the 180 from the feedback itself in order to get the full inversion to 360. And you can only get a crossing like this when you have at least 3 stages. All right. It won't cross with 2 stages. It'll only approach 180. But I can cross 180 if I have 3 steps, because I can go all the way down to 270. So down here somewhere, maybe, is minus 270. Okay. So I can cross over. I'll end up as 270 eventually. That must mean I'm crossing over the 180 point. And so all I have to do then is look up, right, and find out where I am on the amplitude plot. And if I'm above it, that's really bad. That means I'm going to oscillate. And these are called margins. This distance here, right? In fact, this distance here, if I'm not mistaken, is called the gain margin. And these are things that the control engineers are often quoting, the gain margin. They want to know how far the gain margin is from unity. And in fact, they would really like the gain margin. This is the gain margin at 180, okay? They really like the gain margin to be way down here. In fact, I think the rule of thumb is it has to be below 40%. 40% below the unit gain. So that gives you enough leeway. So due to component variation or whatever is happening, you won't accidentally exceed 1. All right. So if you're a control engineer and you worry about oscillations, you will often look at the gain margin and try to find out where is it at the 180-degree mark. Is it above 1? Well, then you're real trouble. But if it's below 1, you want it to be sufficiently below 1 so that it doesn't accidentally go above 1 due to just component variation. All right, so that's the reason why these things oscillate. 2 things. The phase has to be at least 180, and the gain has to be greater than 1. If the gain is less than 1, basically everything gets attenuated, and the little oscillator just can't start up. All right. And you're wondering, you might be thinking, but are you saying I have to inject a sine wave of this frequency in order to see oscillations? No. This frequency, what you have to imagine, in a rail system, there's a lot of noise, all right? There's a lot of noise at the inputs, and these inputs are usually high frequency inputs, and there will be at some place where the system will experience this frequency, and once that happens, it'll hit this, and off it goes. All right. In fact, in a perfect system without any noise, and you're at the steady state, it won't oscillate. It'll just sit there doing nothing, which is why I don't know if you did this, but you could find the steady state for the unstable oscillator, but if you pushed it a little bit, it would start to go out, and you basically gave it enough noise so that it hit this point, and it would start to oscillate. Okay, I think that's all I'm going to do there. Any questions?
You said that the gain margin had to be bigger than 1 by 40%?
No, it has to be you want the gain margin to be 40% less than 1. So, you know, if these were your units, you need it to be at 0.6, I guess.
Okay.
So if you're at about 0.6, that's sort of wide enough. There's enough slack in there that you won't accidentally go above 1. Because you can imagine, you know, these measurements aren't perfect, right? So when you put your actual components in, you won't be exactly at 0.6. So you give yourself enough slack so that you won't accidentally tip above 1. And you know, a lot of systems are not first order or second order. All right, now, I mean, I'm going to shock you now. This system is not actually first order, even though it's got one cascade. From a theoretical point of view, we treat it as a single unit so that the phase is -80. But of course, this feedback loop hides all sorts of things. There's gene expression going on, transcription, translation, and these actually add extra state variables to the system. So this system is actually 3, 4, 5, 6 order system in reality. And in fact, somebody showed that with a single cascade like this, if you did it right, you could actually get this to oscillate too. Because there are hidden state variables in here, basically, which will give you the extra phase shift. And so a lot of systems are like that, right? A lot of rail systems have hidden states, and those states will add, you know, extra orders to the transfer function. And so you'll find a lot of rail systems have the potential to oscillate because they have hidden states. So I suppose a capacitor resistor system is, I guess that's difficult for it to have hidden states, and that probably is genuinely a first order system. But biological systems, due to their complexity, will often have hidden states in them. So it's not so simple in those cases. All right, any other questions? I can extend this video if need be. If there are any areas, I mean, you can watch this video again and again and again, of course. But if there are any parts that were not clear, you can perhaps send me an email, and I'll do an extra 5-10 minute thing on it. So, okay. Any questions, comments? Did this go? How did this go? Do you think anyway?
Well,
Yeah.
it was great.
Oh, okay, good. Okay, we could do it next Tuesday as well if you want then.
Yeah.
Yeah.
Nice.
Okay. And it's nice to get recorded as well. All right, then. If there's no more questions, I think we'll sign off, ladies and gentlemen, all 16 of you.
Yeah. We are in a group.
Oh, I see. So maybe 25 of you.
How about you? 17.
How's that? So you're all catching coronavirus off each other, are you?
Yeah. Yes.
Okay, well, I hope to see you online next Tuesday then. So remember about your assignments. David put his foot down and said, no, you've got to give them to me by 4 o'clock, all right? So try and get them to him by 4 o'clock. If you can't, get them under my door before I come in tomorrow at 8:30. So we can assume they arrived today then, all right? Okay.
Thank you, Dr. Sorrow.
No problem. See you next week. Bye now.